Hey guys, I welcome you all to my channel. A warm welcome from me. I hope you are all doing well. So let's proceed and go on to our third lecture. The topics what I want to teach you here today are given in the video description. So go and check them out first and then come back to my video. So let us begin. Angular acceleration. It's a very simple concept. Just like linear motion, keeping analogy with linear motion, so to say, you can define angular acceleration as the time rate of change of angular velocity. So it is denoted by Greek word small alpha. It is, let us take, at an initial time the particle was in a state which has a angular velocity omega 1. Then after time t it goes on to omega 2 in a state with angular velocity omega 2. So the angular acceleration alpha is omega 2 minus omega 1 by t. If this omega 2 is less than omega 1, then it will be angular deceleration, and if it is positive, then that is angular acceleration, and that will increase its angular velocity as time progresses. So what is its dimension? So when you are determining dimensions and units, you will use just the basic results, that is omega divided by t, for convenience. So omega has a unit of rad per second, time is measured in seconds, so it is rad per second or rad per second square. The dimension is 1 over t square equals to t to the power minus 2, because omega has the dimension t inverse and t is t, so t to the power minus 2. These are very simple things, everybody knows them, everybody knows these concepts. Now what is the relationship between the angular acceleration and the linear acceleration? So in the previous lecture, if you haven't seen it, I will suggest you to go and watch that lecture, that we have derived the relationship in between v and omega not only in magnitudes but also in vector form. So I will give you a suggestion, go to my channel and see the video, then come back. Time once. Now this is the angular acceleration. Oh, just now I have forgotten that I haven't defined what is this. So let us take the particle which is circulating in a circular track, changes its speed by an amount delta omega in an infinitesimally small time interval delta t. Then by definition this quantity is the angular acceleration or maybe deceleration, whatever it is. So limit delta t tending to 0, these deltas are interchanged by d's or the differentials, so d omega dt. So this alpha is d dt of w, and this formula is the instantaneous angular acceleration. So go ahead and replace this. So in terms of magnitude, we find that the a is equals to r alpha, where a is the linear acceleration. Now there is a vector relation which is a equals to r alpha. Remember this, when we will do problems involving vectors in circular motion, you will need this and it will make our life simple. Now similarly you can say that the a is in a plane containing the vectors r and alpha, which is situated perpendicularly to the plane containing a. Now up till now we have done the basic terminologies involved in circular motion. What I want to show you is the analogy in between the variables, or in between the dynamical variables involved in the circular motion and in the linear motion. So first of all, displacement. This is linear displacement, this is circular displacement or angular displacement. So linear displacement is s, denoted as s, and this is theta. measured in radians or degrees, measured in meter, centimeter, pico, deca, you can attach prefix suffixes. So linear velocity, first time derivative of s, which is v, this is first time derivative of theta is omega. Similarly, first time derivative of v and second time derivative of s is linear acceleration. First time derivative of omega and second time derivative of theta is angular acceleration. So using these things and the three relations in between them, s equals to r theta, v equals to r omega and a equals to r alpha, just see putting r you can get all three relations in between the three analogous physical quantities. Using these three, what I have just now rubbed, we can derive the basic equations, kinematical equations involved in the circular motion. So in linear motion, you know what is a kinematical equation, that is v equals to u plus at, where a is the linear acceleration, t is the time t, u is the initial velocity, v is the final velocity. Go ahead and replace them with the circular analogous circular motion physical quantities, that is r omega 2 equals to r omega 1 plus r alpha times t. You can cancel r from both sides and you will arrive the analogous kinematical equation in case of rotation. This is the first equation, pretty easy, right? So we proceed to derive the second relation, which is the s equals to ut plus half at square. So this will be r theta, this will be r omega 1 t plus half r alpha t square. Go ahead and cancel r from both sides and you will arrive the second kinematical relation in the rotational motion or circular motion. And the last is v square equals to u square plus 2fs or as. Go ahead and cancel r square from both sides. You will arrive onto its rotational analog. So these are very simple equations but profound equations. We will use them as much as we can while dealing with the numerical problems. So remember this in mind. So guys, you have come to an end. We have come to an end of our video lecture. I think this is the third lecture. I will be posting more lectures like this. So if you like my videos, go ahead and subscribe to my channel, and oh yes, press the bell button